different food.
Okay, so let's start the second lecture for the Renzi about three-dimensional topological quantum field theory.
Thank you very much. And yeah, so yesterday during my first talk, I tried to explain a little bit what I mean by topological quantum field theories in the three-dimensional case in general, and also in an extended version of this notion, extended TQFTs, which will be kind of the ultimate goal for this series of talks. But today I will mainly discuss one specific version of a three-dimensional TQFT, which is the building block for the whole construction. And this is a functor defined on a certain strange category of connected cobordisms between connected surfaces with connected boundary. This is what I called yesterday Crane-Yetter cobordism category. And this is, well, a subcategory inside the two category of three-dimensional cobordisms is a subcategory of the morphisms from the empty one-dimensional manifold to a single circle. So objects in this category are surfaces with one outgoing boundary component and zero incoming ones. And if you consider the connected objects and the connected morphisms between these, you get a somewhat strange category that has a monoidal structure and even a braiding, but it's not the one of the ambient two category. This is not induced by disjoint union, and the braiding is not induced by just re-indexing. It's not the symmetric one. This is rather induced by boundary connected sum, and the braiding is non-symmetric. So today I will start. So my initial goal will be to tell you how to think about these cobordisms in a very pictorial diagrammatic way. So how to represent them through diagrams, and how you don't need to understand really the cobordisms themselves and the strange extended structures they have on them, like Lagrangian subspaces and signature defects, if you're happy to just understand diagrams and how they compose. Okay, so I will explain why this category of three-dimensional cobordism is equivalent to a category that I will call 3KT. This will be the category with objects, natural numbers. So this would be a skeleton of this category of connected cobordisms by Crane and Yetter. So connected surfaces with one boundary component, they are, well, essentially classified by their genus. So we can get a skeleton of the category by just taking objects to be natural numbers. And the idea would be that there will be a surface sigma of genus G with one boundary component that will be a parameter, like that will correspond to the integer G. Then morphisms in this category are, okay, morphisms from G to G prime. What are they? They will be equivalence classes. So let's call them G prime Kirby tangles T in the genus G handle body MG up to frame Kirby unit. Okay, so I need to tell you what these are, what Kirby tangles are, and what frame Kirby moves are. So I will try to give a definition by example. Hopefully, this is clearer than writing a long definition. So this is a picture, an example of the genus 2 handle body. So in this picture, you see M2, and this is realized as the cylinder over a single disk. And to the bottom face of the cylinder, I glued 2 copies of the 3-dimensional 1 handle. Okay, and we're going to represent this diagrammatically by looking at a slice of this handle body, a vertical slice, the intersection with a vertical plane that cuts in half all the handles, right? So genus 2 handle body in this configuration can be understood as a 3-dimensional cobordism with corners from a surface of genus 2 on the bottom base with one boundary component, which is this big circle, to the surface of genus 0 on the top, again with one boundary. Right. So
the attention disks are not corners for you, right? So they are sort of
right. So here you can smooth corners here and here. Right. It's not worth to smooth corners here because keeping corners of manifolds with corners allow us to have a nice notion of horizontal composition. Yes. But yes, so and then 3 curvitangle in the genus 2 handle body, for instance, is something like this. So what is this? In green, we have a tangle. To be a curvitangle, you need, okay, you are allowed to have both circle closed components and arc components, but all the arc components are required to connect 2 adjacent endpoints on the top boundary of this handle body. So this tangle is allowed to have endpoints, but only on the top boundary of the handle body, and every component connects one endpoint to the one just next to it. Okay, so you have an even number of endpoints on the top, and you're allowed to have closed components, and your tangle can move around your handle body, and this is what I call a 3 curvitangle because the arc components are 3, and it's inside the genus 2 handle body. So this will represent the morphism from the number 2 to the number 3, because you can understand this as a cobordism from the surface of genus 2 to the surface of genus 3. I will explain how to do this, but basically already I can tell you that if you think of the arc components as tunnels you are carving out from the handle body, you will see that the top base of this picture, the 3-dimensional one, I will always represent this projection on a slice, but the 3-dimensional picture, you can see appear on the top a genus 3 surface whose handles are kind of embedded inside the handle body in a complicated way. And there are also closed components. Those you don't actually just remove them. You also need to glue them back through an operation that's called surgery. But if you don't know the topological operation of surgery, I will tell you all the diagrammatic rules you need to know to have a category which is exactly equivalent to the category of 3-dimensional by Crane and Yet. Okay, so frame Kirby moves are these 2 moves. Whenever you see a closed component that comes with a meridian, so a small unknot that only encircles the component and nothing else once, you can remove the pair. This is a canceling pair, and it can be thrown away without changing neither the cobordism nor the signature defect. Okay, and the other move, the second one, is whenever you see a closed component and another component that can be either closed or an arc, whatever you have, you can slide the R component over the closed component, and I have dots here, which means that the sliding should follow the framing of the component. So for instance, if you have, let me draw an example, if you have the closed component below that is, let's say, that is knotted, right? So let's do something like this. Okay, and you want to slide an arc over it, you should follow the framing specified by the picture, like this. It should be parallel in the plane. Okay, so this is the operation of sliding the top over this one. Okay, and if you consider the pictures I've shown before, up to these two operations, all the possible pictures like the one I've shown before, you get a category which is equivalent to the category of Crane-Yetter. So composition in this category is given by gluing pictures one on top of the other, like cobordisms glue. So what you have to do if you have a morphism from 2 to 1 like this, and you want to compose it with a morphism from 1 to 2, is you stick one picture on top of the other, but the tunnel that you have in the bottom picture should be filled with whatever is inside the handle of the top picture. Okay, so in this case, on the top, I have two parallel components that run through the one handle, and they should be inserted in the R component here on the bottom. So this is the strange composition between the two cobordisms on the left, right? And this is what the identity looks like for genus G surface, or the number G in this category. This is what the tensor product looks like. As I said yesterday, the tensor product in this category is induced by boundary connected sums, so gluing a pair of pants around the circle boundaries of these two morphisms. What you get is you stick diagrams one next to the other and get the tensor product. This is what the braiding looks like, and now the braiding is not symmetric braiding like in the standard category of cobordisms, is non-symmetric because the equivalence relation on diffeomorphisms on cobordisms has like is induced by diffeomorphisms that preserve the boundary identification. So the S1 in the boundary of object is not allowed to be moved. So you cannot undo this tangle to the identity. And oh, sorry, I went too far. So this is all you need to know basically to work with the category of Crane-Yetter cobordisms, right? And my goal will be to explain how to define TQFT, the Kernel-Lubashenko TQFT, on this category. Yes. And I will start by focusing on a subcategory of this one, which is which I will denote here 3TT, which is the subcategory of top tangles. This is going to be the subcategory of Kirby tangles that do not have closed components, only have the arc components. Morphisms have no closed components. Right? And the first result I said out loud, but I will write down in a second, is that this category is equivalent to the category of Crane-Yetter cobordisms let me start by writing it just below here. So then I will show a few more pictures, and I will remove the slides. So the first theorem, I hope it's visible here, is that the category I introduced yesterday, cobordisms by so craniator cobordism, is equivalent to 3KT, and the equivalence is what I explained before. So if you have a Kirby tangle and you want to get a cobordism out of it, you just carve out, you dig tunnels following the top tangle components, and you have to do this topological operation on closed components called surgery in order to get a cobordism from a genus, well, G surface to a genus G prime surface with one boundary component. And you have a signature defect attached to every cobordism. You get just the signature of the closed components in your diagram. And you don't actually need to know the definition of this functor if you're happy just to know that the two categories are equivalent. So understanding working with this one is equivalent to working with the category of cobordisms. And what I can show you now with these pictures is a result by Klein and Yetter, maybe by just Yetter originally. Which is the fact that the surface of genus 1 with one boundary component is a Hopf algebra. In the craniator cobordism category. So the object 1 in the category of Kirby tangles is a Hopf algebra in this category. So what do I mean by a Hopf algebra? Maybe everybody knows, but here is a quick reminder. So a Hopf algebra is an object in a braided monoidal category that comes equipped with a set of structure morphisms. It comes with a product, with a unit, with a coproduct eco-unit, and an antipode with its inverse. I represent these through these pictures, which should be read as yesterday I was doing for the grading. They should be read from bottom to top. And when you see 2 points, one next to the other, you should read the tensor product. So the trivalent vertex you have for the product is a morphism. You should understand this as a morphism in the category in the ambient category from the tensor square of an object to itself, to the object. And then when you have no point, it's just the tensor unit of the category. And with these pictures, you can state the axioms that Hopf algebra should satisfy by diagrams. So the first diagram will tell you that the product is associative. So taking the product of two components and then multiplying the result with the third component is the same as first doing the product of the second and third and then multiplying the result with the first. The second axiom will tell you that the unit is a unit because a straight line represents the identity of an object. This is the dual axioms for the coproduct and the co-unit. So the coproduct is co-associative, the co-unit is co-uniton for the coproduct. And these are the axioms that tell you that the two algebra and coalgebra structures are compatible. They form a bi-algebra. So co-unit of a product is a product of two co-units. The unit, so the coproduct of a unit is the bunch of units, and this is the kind of the compatibility between product and coproduct. And the axioms satisfied by an antipode are these. So multiplying the two components of the coproduct of an element, one of which has been applied the antipode to, then it gives you co-unit followed by unit. And the antipode is invertible. So this is a Hopf algebra, and if you've seen any construction in quantum topology, you've probably already met Hopf algebras because they're everywhere in quantum topology. And why are they everywhere in quantum topology? Well, a topological reason for their omnipresence is that this category of cobordisms that I'm focusing on has a monoidal generator, which is a Hopf algebra itself, already in the category. And the structure morphisms for the Hopf algebra structure in this category are these ones. This is a product, this is a unit, this is a co-product, a co-unit, and the antipode with its inverse. And it's an exercise to check with the composition rules that I had before and the relations provided by well, actually, so you don't even need framed Kirby moves here, because framed Kirby moves only tell you how to modify a Kirby tangle which has closed components. If you don't have any closed components, the only moves you need are isotopies. So you can check that this is a Hopf algebra just by doing isotopies on compositions of tensor products of the generating morphisms. Okay, so this is a Hopf algebra, and now I can tell you. So now the goal for explaining, so in order to explain how to construct the Kelvin-Lukashenko TQFT, I should tell you how to represent this category, and in particular this Hopf algebra, in some well-chosen target, and I will use a modular category to do this. So I will start using the blackboard now. Maybe like this. Yes, I think. So basically, I've told you now, like I had a statement on the blackboard yesterday and I haven't written it down again today, but my goal is to construct a braided monoidal functor from this category here to some linear category. I will take a modular category. So what is this? Let me define it in stages. So a category C is a k-linear category C. Is finite if it's equivalent as a linear category to the category of A modules for a finite dimensional algebra, like K algebra. A, which is not given, but this is a kind of a concise way of stating a bunch of finiteness conditions. So it's a category with a finite dimensional home spaces. So spaces of morphism in objects are finite dimensional, finite number of simple objects, finite length. A bunch of finiteness conditions are all implied by this equivalent formulation. But this is kind of like the algebra is not given. It's just a category is finite if such an A can be found. And we will work with finite categories and a monoidal category is said to be left rigid if every object in it admit a left dual. And the left dual is another object that comes with duality morphisms. So with an evaluation and the co-evaluation that satisfy the zigzag equation. But yes, in the category of vector spaces, it's just the linear dual for finite dimensional vector spaces. And I will have two main running examples for this construction. One will be semi-simple categories, and the other will be categories of representations of some Hopf algebra in vector spaces. And in the category of representations of Hopf algebra, the dual is defined using the antipole. So it's the linear dual, but the action is defined using the antipole. But if you have a finite and rigid category, then this admits a very important object, which is called the end of a certain functor that I will denote by using this notation. This is an object that satisfies a certain important universal property, but instead of telling you exactly the property, let me tell you that this you should think about this as being an object. What is this? Is an object. I will make examples in the two. I will describe it in the two examples that are going to be important for the construction. So it's an object E that comes equipped with a family of structural morphisms. Of this form, one for every object in the category. And this family of morphism is dinatural. And dinaturality is some sort of external naturality condition, which again is the important thing will not be to know the complete definition, but it will just have in mind concrete examples for such an object. So first of all, you should know that every finite left rigid monoidal category admits a unique and of this form. to isomorphism. So it's an object defined by a universal property. So this means that when it exists, well, it's unique up to isomorphism. And the examples to have in mind are, let's say that C is a finite left rigid monoidal category. So the two running examples I will have is when C is semisimple. Semisimple means that every object in this category is isomorphic to a finite direct sum of simple objects. And simple objects are those which have one-dimensional endomorphism space in this definition. Okay, and C is semisimple, and I use this. I choose this as a set of representative of isomorphism classes of simple objects. C. Then the end is going to be this object. So if the category is semi-simple, so every object is a finite direct sum of objects in this list up to isomorphism, then the end can be described very explicitly as a finite direct sum of tensor squares of simple objects, basically, well, objects under dual. And we can also write down explicitly what are the structural morphisms, but I will not do this because for time constraints. I will rather tell you what is the other example to keep in mind. Is the category C of H modules for H a finite dimensional So I explained what is a Hopf algebra in a general braided monoidal category using pictures before. In the category of vector spaces, you get from that definition the classical definition of a linear Hopf algebra. And by the way, one could, so since our goal is to define a braided monoidal functor from a category which is monoidally generated by an object, which is a Hopf algebra, one could try to map this category 3KT directly into vector spaces by sending the object to a Hopf algebra, maybe looking for the conditions that this Hopf algebra in vector spaces should satisfy. But I know virtually no examples of interesting functors constructed this way, mainly because the Hopf algebra here comes with is a Hopf algebra in this braided monoidal category where the braiding is non-trivial, and in vector spaces you have a trivial braiding, symmetric one, and this choice for the construction would inevitably yield very trivial functors, representations. So there is a magic trick that we will apply, which will turn a Hopf algebra in vector spaces into a Hopf algebra in another category. And this one will be kind of the main application, the main example of this construction. And here is the first ingredient for this for this strategy is the fact that the end, this universal and very important object in the category of H modules is the Hopf algebra itself, is the adjoint representation. So a finite dimensional algebra can be given the structure of an object in its category of representation, meaning it can be equipped with an action of itself, onto itself. And when this is a Hopf algebra, you have several possibilities for this action, and it turns out that the most relevant one for the purposes of this construction is the adjoint representation. What is this? So by definition, the adjoint representation is defined by this formula. So if you have an element y, so the adjoint representation is the algebra itself, which acts onto itself. In this notation, I'm using some classical notation due to Swidler. So this is the same as taking the coproduct of, so this means taking the coproduct of x, multiplying from the left with the left component of the coproduct, and from the right with the antipode of the right component. So in diagrams, it's something like this. Okay, this is the adjoint action, and right. So this is the end of the in the category of H modules, and these would be kind of the two main examples. And I will so we will look at finite rigid categories. We will actually look at ribbon categories. So what's a ribbon category? It's a left rigid braided monoidal category. That comes equipped with a twist. The twist is a natural transformation of the identity functor of C, which is self-dual. Self-duality means basically that, well, this condition, but it will not be, so the main takeaway, again, like the details of the definition are not as important as the diagrammatics that is allowed from these notions. So if you represent in a ribbon category the twist by a kink, then together with the convention of representing braiding as a crossing in diagrams, the axioms of braiding will tell you that the crossing gives you diagrammatic calculus that is invariant under Rademacher 2 and Rademacher 3 moves, and the self-duality of the twist will tell you that the diagrammatic calculus is invariant under Rademacher 1, the remaining. The framed version of the Rademacher 1 move, which is the following. So if you have a kink and also the other one composed with each other, then the result is just the identity. So and yes. So basically, in a ribbon category, you can represent. So a ribbon category is a category that comes with a monoidal structure, so a tensor product. You can tensor together objects and morphisms. A braiding, naturalized morphism between tensor product and the opposite tensor product. And duality, which allows you to orient edges in the diagrammatic calculus with the convention that an upward oriented strand represents the identity on an object, for instance, and if you orient it downwards, you are representing the identity of the dual object. And the twist allows you so if you represent it by a small kink, then it's compatible with the braided structure and the duality, and you are free now to think about morphisms in a ribbon category as frame tangles. So pieces of strings with a framing that you can deform by isotopies that preserve the frame. And again, we have so there are many examples of ribbon categories. The main of course, there exist semi-simple ribbon categories that are just ribbon categories like this, which are semi-simple. But for Hopf algebras, if H is a ribbon Hopf algebra, which means this is a classical notion. This is a Hopf algebra equipped with an R matrix, which is an element in its tensor square, and the ribbon element, which is a central element related to the R matrix. Then H mod is a ribbon category. And there are plenty of ribbon categories that arise this way. The main family you can keep in mind is small quantum groups. Of some complex Lie algebra G at a root of unity, at a suitable root of unity. Zeta. For instance, the simplest example you can keep in mind is quantum SL2, if you know it. If you don't know it, unfortunately, I will not have too much time to go into the details of concrete examples. I would just like to say that there exist families, infinite families of concrete examples of such Hopf algebras, which can be explicitly, completely figured out. All the relevant pieces of structure that intervene in the construction can be presented by formulas, and computations are can be made very explicit. So there is so this whole construction admits a lot of very concrete examples. Okay, and if you don't know them, I will not have time to discuss them. It takes too long. But just know that there is a lot of explicit details that can be found on these. So now I can state my first proposition for today. If C is a finite frequent category. Okay, I will do this actually, because now I will need to lower the screen again. So I will write it down here and hopefully it will not be covered. So proposition. If C is a finite ribbon category, so every such C induces braided monoidal functor that I will denote with a J. And this, at first, let me just define it on top tangles with target C. And this would be a functor that sends the natural number G to the G's tensor power of the n. So assigning the n to its tensor power G to every natural number can be so this this association can be extended to a braided monoidal functor. So let me explain why, how. So the basic idea is that top tangles. So top tangles, I remind you, they are those Kirby tangles that I draw in examples before that do not have any closed component. So they are just composed of these R components that join two adjacent endpoints on the top of a handle body. And whenever you have a top tangle T, let's say in a genus G handle body and with G prime components, this is a morphism from G to G prime in the category of top tangles in handle bodies. And whenever you have such a, so this the definition of this functor requires you to well, if you take this as a definition for objects, if you want to map the object G to the G tensor power of this universal object, the n, inside your finite ribbon category C, then I need to tell you where to map top tangle T of this form. And you can start by considering a regular diagram, let's call it, for this top tangle, which is just like any diagram for this tangle where nothing happens inside the handles. And if you start with a diagram where which looks complicated inside handles, just choose a disk inside your one handle that intersects a finite number of non-singular points of your projection and isotope, like just use an isotopy of a small color of this disk to push everything that is complicated inside the one handle into the box that I labeled T tilde inside my diagram. And this will give an isotopic diagram to the original one, which represents the same morphism, but which has nothing complicated happening inside the one handles of the handle body. Okay, but in general, inside one handle for the handle body, you can have many strands of your top tangle that pass through. And I claim that you can understand such a diagram as a dinatural transformation. A dinatural transformation, I haven't said what this is before, but I should have said. So let me write it here. Morphism like the one I like the one for the structure of the end, for instance. A family of morphisms defined of this form, one for every object, is dinatural if you have this, if you have that F tensor, so F tensor, the identity of X prime, X dual, composed with the morphism attached to X is the same as the identity of Y tensor X dual, composed with the morphism attached to Y for every F morphism from X to Y. So basically, a dinatural family of morphism has target objects of the form X tensor X dual in this case. And if you look at the morphism with target Y tensor X dual, which is obtained from the morphism attached to X by composing the left component with F, with the morphism F from X to Y, then this should be the same as looking at the morphism attached to Y and composing the other leg with the dual. So basically, if you have a dinatural map, then it satisfies this in diagrams. So here you're starting from some object, for instance, the end. Here you have your object X, and here you need to switch to your object Y. So basically, you can think about the morphism being allowed to pass from one side of the other of this dinatural family of morphisms, much like you can do with something that can travel along a one handle. A one handle is some sort of dinatural transformation, you can think in topological terms. And to make this more precise, you can think about orienting every edge in my top tangle T counterclockwise. So you start from one endpoint on the top, and you orient counterclockwise from right to left. And you can choose arbitrarily labels x1 until xg prime, given by objects in your category C, to attach to all the strands. Each is attached to the corresponding strand. And what you get by restricting to T tilde is a morphism that has this as a target and has some source which is determined by whatever goes inside the one handles. And up to isotopy, these objects are not fixed. An isotopy can change what these objects are, but once you fixed the representation T tilde, the regular diagram T tilde for your morphism T, then these objects have been fixed by x1 and xg prime, and you can pre-compose them with structure morphisms of the end. And what you get is a morphism which is dinatural in each variable, which means that if you stick one box with label f on top of this edge, for instance, on the top that goes to some y prime, then you can isotope this box all along the top tangle and have it appear on the right with a jewel on its label. And this will tell you that this morphism over here is dinatural in this first variable. And this applies to all variables. And the universal property satisfied by the end. So by very definition, this magical object that I'm choosing as the image of all the objects in my category of the top tangles, the universal property it satisfies will tell me that there exists a unique morphism, which I call JC of T, that satisfies this identity. And this association is from a regular top tangle, from a regular diagram of top tangle to this morphism, does not depend on the regular diagram I chose for my top tangle. Different choices yield the same morphism here. And these morphisms are functorial. So the composition of top tangles is translated into the composition of these morphisms over here. And it's also braided monoidal function. So it behaves well with respect to boundary connected sum. It's translated to a tensor product. And the braiding is also respected. So I don't know when did I start.
You have like 2 minutes. Maybe.
I have 2 minutes. If I have 2 minutes, it's probably better to just state one corollary of this. The corollary of this. So I don't claim that the proof I'm sketching here is complete of all details. Okay, of course. But what I want to what I wanted to try to explain is the general idea behind this. So there is a certain very special object that exists in any finite ribbon category, which is defined by some universal property, and it's called the end of this functor considered by Libashenko. And this object can be described in very explicit terms in the 2 running examples, for instance, that we're going to look at also next time, which are semi-simple categories and categories of representations of a finite dimensional top algebra. And this object satisfies a very important universal property with respect to dinatural transformation with this target. It's the universal one. So whenever you see a cubordism like this one, where you have no surgery happening anywhere, so it's just a top tangle, you get for free, by the universal property satisfied by the end, a morphism between tensor powers of the end. And this is because top tangles are precisely, so they are built to satisfy this dinaturality property that will produce for you such a unique morphism. And the corollary here is that the end in a finite ribbon category is a Hopf algebra. For every modular, for every finite ribbon category. See. So if you have a finite ribbon category, then its N is a Hopf algebra. And its Hopf algebra structure is defined by taking the image under this functor of the Hopf algebra structure that it already exists in the category of three-dimensional cobordisms by Crane and Young. Okay, so this gives you a recipe to turn a Hopf algebra in vector spaces, which which lives in a category equipped with a symmetric braiding, into a new Hopf algebra inside a different category, its category of representations, which is itself braided if the original algebra comes with an R matrix and with a ribbon element. As an object, this new Hopf algebra is called the transmutation. Looks exactly like the old one. It's the same vector space. It's equipped with the joint representation, so it has the structure of a modulon itself. And almost all its structure morphisms. This is another exercise that I could leave, but that can be figured out by explicit computations. The Hopf algebra you get in the category of representations of H has the same product, the same unit, the same co-unit. You need to change a little bit the co-product and the antipode to make them into intertwiners for the joint action. But basically, this is some sort of procedure that will, starting from a Hopf algebra in vector spaces, give you a Hopf algebra in its category of representations that is going to be the heart of the TQFT construction. And next time I will tell you how to extend this to morphisms that have to arbitrary morphisms in Kirby tangles, and also maybe try to say very quickly what is the strategy for extending this to a full extended TQFT, to an extended TQFT in dimensions 1, 2, and 3. But I will stop.
Questions?
Yes.
Could one extend this to also include like additional tangles which are colored in the category C? So it's like a mix of this functor with the.
Absolutely. I'm not doing this here just because I haven't had the time to talk about ribbon graphs and bichrome graphs in general, but this you can imagine having inside these cobordisms also ribbon graphs labeled by objects of C, maybe with components of two different natures, like certain components that needs to undergo the same procedure as these green components here, like the red components in bichrome graphs, and the blue ones that can be treated just like Drive does.
So in a sense, it's like an extension of the heuristic Dreieck functor from tangles to the braided category. So it's like the graphical calculus for ribbon categories which allow for ends.
Yes, exactly. Yes, absolutely.
More questions?
Is there a specific reason why you prefer ends with respect to co-ends, or?
No, it's just a matter of conventions. So if you prefer co-ends, you can choose, instead of choosing handle bodies with handles on the bottom, you can choose handle bodies with handles on the top and draw bottom tangles instead of top tangles. And there is so we would the TQFT construction goes through under an additional assumption which will tell you that the Hopf algebra is self-dual. And in this case, the end and the co-end for this category, they are isomorphic. And the two constructions coincide, they are isomorphic. They give isomorphic TQFTs. And And the universal property satisfied by the coend will give you a functor that looks exactly the same, but with pictures reversed. I started using ends instead of coends because this reduces the number of dualities you consider. Also because, like, when the kind of main example for a coend is the co-adjoint representation, so you need to consider the dual of an algebra with, and also because there are two like Lyubashenko and Kerler always work with the coend, but Javiero, for instance, always worked with the end, even though he draws bottom tangles because he reads them. But, okay, but his convention is to work with the end, and if you have a preferred convention, you can, so they are equivalent, so they can be exchanged. You just need to make this coherently throughout the whole construction.
Did you say something about properties of this functor?
Yes, so it's a braided
JC.
monoidal functor.
No, but how much it's surjective? Because there are cases, for example, if C's happen to be pointed, then the image of the factor is just tensor U.
Pointed meaning
Every object is invertible.
so every object is invertible?
No, I assume semi-simple pointed. Yes, yes.
Okay. Yeah.
And
So
graded vector spaces.
So, well, this
this
functor hits only tensor powers of the coend of the end. Sorry.
Yeah.
So this is on the level of objects. This is all you get.
So it doesn't need to be surjective, for example.
No.
But it would be if you include the extension.
Ribbon
by
graphs, of course,
the
of
blue
course,
lines, if you add these and right.
of course.
Yeah. Then you would have a tail for
Yeah.
projectives, and then
You can make it surjective by adding whatever you need.
yeah. Okay.
Okay, so maybe we can close the session and go to lunch. Thank you again. So if you don't have a lunch ticket, you're here. I think that is fine.